now.
Okay.
Okay, so everybody, it's a pleasure to... Sorry?
Is anybody recording this?
Should we?
Do you want me to?
No. Richard, what do you think?
I can record it. Let me quickly... Okay, so it's recording now.
Actually, what? Oh, you're recording. Okay.
Yeah, I can record it from here, and then if we could distribute this somehow, so...
Yeah.
If somebody wants. Okay, sorry for the interruption.
Okay.
Okie doke.
All right, everybody, it's a pleasure to welcome you all here tonight for our May ASTROnight. And it's a pleasure to introduce Richard Camuccio, who's going to give us our presentation today. Richard's a first-year graduate student, and even though he's been here in times of isolation, he's already made his presence well known in our outreach activities and at our campus observatory as an assistant. And today he's going to talk to us about extrasolar planets. So whenever you're ready, Richard.
Thank you, Tom. Thank you, everybody, for being here. And this is really exciting. It's the first time I'm giving a presentation from my living room. And I would much rather be doing it at the observatory, but we wouldn't have been able to see much. So instead, what I'm planning to do is to show what you could observe and how the process of setting up that observation. In particular, we're going to be trying to understand how to find an exoplanet, so a planet orbiting another star. And in particular, the exoplanet that we're going to be looking at tonight is known as the waterworld, officially, actually, Gliese 1214b, and some interesting physics with that system. So it wouldn't be a talk about exoplanets without starting with Giordano Bruno, who, as far as I know, really put together these thoughts almost 500 years ago. So it goes to show people have been thinking about these ideas for a very long time, and they were dangerous ideas at the time. So Giordano Bruno lost his life for expounding ideas like this and other ones, but these are his words. In space, there are countless constellations, suns and planets. We see only the suns because they give light. The planets remain invisible, for they are small and dark. There are also numberless Earths circling around their suns. And if you look at the date, 1584, I think that's pretty crazy that people were saying these things back then. Remember that this was the time when Kepler was first deriving his laws of planetary motion. Galileo was soon to point the telescope at the sky. So this was the beginning of astronomy. And Giordano Bruno, I think, takes credit for at least a lot of these ideas about exoplanets. So the picture behind is a very famous one, but it's, I forget, I actually have the title here, around here, but basically the idea is the celestial sphere, and this is some human, perhaps an astronomer, looking for truth beyond the celestial sphere. And if you've actually been to Rome or you've seen similar paintings around this time, this is actually an etching, a wood etching. And this wheel within a wheel at the top left is a very common idea that you see around that time. This is the beginning of when the deist view of the universe was first starting to come into play. These were the early moments of those ideas. So the clockwork god, the fact that there are laws of nature, this was all kind of brand new at the time. It was the birth of physics in a sense. And so exoplanets have been kind of at the forefront since the beginning of physics in a lot of ways. But it's taken a very long time to find them. Why? Because they're very difficult to find. As Giordano Bruno said, there are these very small dark dots orbiting very bright stars. And I heard an analogy once that if you're trying to find an exoplanet, it's like trying to look at a building with 10 windows on a side and 100 windows up, and they're all open and they all have lights coming like out of their windows, and somebody pulls the shade down a third of the way on one of the windows, and you're supposed to tell me how different the brightness is of the whole building. So that amount of sensitivity is why it's taken 500 years almost to find these things. But we are now in the era of exoplanets, which I'm hoping to show you. So how do we find these? The primary way that we had since the beginning, since the late 80s, early 90s, is known as the radial velocity or Doppler method. And it's involving gravity. Basically, as a planet orbits its star, really they're orbiting around a center of gravity, and there's a mutual interplay between gravitational forces. So as the planet sweeps around, there's a wobble induced on the star. So the star gets pulled a little to the left and pulled to the right. And the reason why it's called the Doppler method is because when you're looking at these stars and they're coming towards you or they're moving away from you, something very similar to the Doppler effect when it comes to sound happens with light. So at the bottom here, this is a spectrum of the star. This is the chemical elements, the distribution of materials in the star. And you can see that it shifts to the right and then to the left, depending on where the planet is. The idea here is that you can measure that displacement and you can tell how massive that planet is. This really works well for only certain types of planets, particularly ones that are massive and very close to their stars. So for the first decade or so of exoplanet detection, we were only finding Jupiter-type planets orbiting very close to their stars, orbiting in mere days. And so the population was heavily skewed toward those. It wasn't until the advent of more modern technology like CCD technology, digital camera technology, better optics, that other techniques came into play. The other main technique now, and actually the predominant technique that's discovering these planets, is the transit technique. And this is the one that an observatory can use on the ground. This is the method that I'm going to be describing today. Basically, the idea is, stars are positioned all over the sky, and we know now that they pretty much all have planetary systems. But only certain ones might be oriented in such a way where the planet actually passes in front of the star. This actually is a good number of them regardless, so we can find thousands. We found over 4,700 confirmed exoplanets within a very small area of the Milky Way galaxy, basically in our backyard, if you want to talk about relative distance. And so the idea here, this picture, is you have a planet passing in front of the star, and it blocks a little bit of the light from that star. So we can observe what's known as a transit, and we can measure some properties of that transit and tell you not about the mass of the planet, but the size of the planet. So if you have both methods, the Doppler method, which gives you the mass, and the transit method, which gives you the radius, then you can deduce something about the density of the planet. Once you know the density of the planet, you can deduce other things like, well, what types of materials exist at that density? If we know how far away the planet is from the star, then we know its temperature. And so we can learn a lot by including both of these methods. But the one available to ground-based detectors, at least like ones like the observatories, is the transit method. Now, this is a pretty picture, and you might not believe me, but we've never actually seen another star before, ever. We have never been able to see the surface of another star. They're so far away. What we do wind up seeing is something like this in a picture, which is a very pixelated rendition of a star. This is actually a kilonova in particular. This is data that I had from many years ago. It's a type of stellar death. It's an explosion like a supernova. But regardless, you're going to have a digital camera taking pictures over time of a star. So if you know that the planet's going to pass in front of the star, then you can take picture after picture, measure the brightness that you see on the camera, and you should be able to see a dip in that brightness for a limited amount of time. And that dip is what tells us the physical properties of the planet. So a lot of techniques going into this is known as photometry. It's one of the most basic measurements an astronomer can make, which is photometry. It's the amount of light coming into your camera. So it's a very basic idea, but the techniques involved can be a little bit difficult, especially at the sensitivity that you need. So how does a digital camera work? Well, this is taken from a magazine from, I think, 1983, when CCDs were first coming onto the general market. They weren't that good at the time compared to the way they are now, but the idea is it's an old analogy of the red solo cup. It's called the red solo cup analogy. Basically, if you have a water balloon and you don't know the amount of water in it, there's a volume of water that's unknown, and you hold it over an array of cups, you pop it, and the water flows into all of them. The idea of the CCD is very similar. You have some brightness of a star which you have to characterize, and photons fall from that star onto your camera. So in a similar way, you can then take each of the pixels, each of the buckets, and pour them out and then measure the total amount of water you collected. And so that's known as the flux of the star, because it's the amount distributed over the area of that chip, if it's a digital camera, or in this case, a bunch of buckets. So the way the CCD camera works is the photons fall into the buckets, and then the CCD is read out. Now, all the buckets are dumped into a serial array like this, and then the serial array is read by the computer, and you get a value of brightness in digital units. So this is the basic idea. The CCD that we use on a telescope is pretty much the same type of CCD in your digital cameras. The only difference is that each pixel on your digital camera is sensitive to red, green, and blue. The ones in astronomy are only sensitive to a single value of intensity. because when you split up across a bunch of colors, you actually lose sensitivity. So we're trying to maximize the sensitivity we have by reducing the amount of color to a single value. So that's how the camera technology actually works, in analogy at least, but hopefully that gives a rough idea. And so what you would then do is make a plot. So remember, the planet is passing in front of the star, and there's a limited amount of time this happens. So the idea is you're taking picture after picture after picture, and you measure the brightness of that star over time, and you plot it. So time is to the right. So the beginning of your observation is at that y-axis there, and then the observation duration goes to the right. And brightness, so the brighter something is, the higher it is on the graph. So you have a star here, this big circle, and you have, I have 4 snapshots in time. Basically, the moment the planet starts to pass in front of the star, so it's coming out from behind the star and starting to pass in front. The moment it just completely covers the star here, and then the opposite, the last moment it's in front of the star, and then the moment it finally leaves the star. So this is known as ingress and egress. And so when you know these times and you make this measurement, you should get a dip. And this is a very idealized picture, right? Because we're just imagining circles covering each other. So what you'll wind up getting is some sort of very geometrical curve like this, where in reality they're usually curved for more complicated reasons. But from this curve, you can measure a bunch of different properties directly. One of them is tau, which is the width going from max to when it first reaches the dip. And that tau is both the same in ingress and egress, at least that's the assumption. Then we have TC, which is the center time. That's the time that the planet is at the center of the dip, the deepest part. That's actually very important because that tells you the radius of the planet, essentially. Then there's delta. Delta is the actual depth of that transit that we see. So how bright is the star normally, and then how bright is it at its minimum when the planet is blocking the most amount of light possible. And then the fourth one is T. Now, if we know delta, which is the depth, T is half of that depth, and then how long it is from left to right. So that's the transit duration. So you have 4 values, T, TC, tau, and delta. And that's the maximum amount of information you can read from a light curve. So I would get those 4 pieces of information, and then when I compare them to that Doppler shift measurement, I can get the mass and the radius and figure out all the physical properties of the planet. So I'm going to actually explain just one. This is the only equation that we really need to understand today, because delta is the simplest measurement you can make to give you information about the radius of the planet. So this is known as the mass ratio, or the radius ratio of the planetary solar system. And just by measuring delta and taking the square root, you get this ratio. And I'm going to explain where you get this from. This is not just random, okay? So, by the way, so the left side here is the physical property. It's the planet-star radius ratio. And the right side, delta, is your transit depth. So you have a physical property on the left, which comes directly from an observable property on your light curve measurement on the right. Okay, so that's why it's very simple. You know delta, you can immediately get a radius ratio. And, if you know RS, that's the radius of the star, from another measurement, then you actually can immediately get an estimate of the radius of the planet. If the radius of the star is not known, then you have to do some special modeling and figure out, basically, if we know the mass of the star, then we can kind of estimate the radius based on its color. But that's more advanced. So really, we're going to assume here that we know the star's radius, we can measure delta, and then we can immediately get RP, the radius of the planet. So the way this works is if you consider a planet as a circle and the sun or the star behind it, the ratio is given, okay, so that we know the area of a circle is pi r squared, so the area of the star is pi rs squared, and the radius of the planet is very similar, it's pi rp squared. And so that transit depth is given by a ratio of the areas, right? So if I take AP over AS, pi r squared, pi's cancel, and I get RP RS squared. If I take the square root on both sides, I return to this equation. So this is why it's a simple ratio of areas, but it's a very powerful method. So it's why it's revealed a lot of information since it's been used. So, by the way, these are the other 2 equations. This is why I'm not going into it, but just so you know, delta T tau on the right, T, tau, delta, and the period of the planet, which we can measure and get these other physical properties on the left. but that's beyond the scope of this talk. So I'm not going to go into these two, but those three equations are the ones that you would get from this measurement. Okay, so this is the one we'll focus on. Okay, so how do we actually make this measurement? Well, measurement, it's interesting. You can use, so this is actually TTU's observatory. On the left, we have a 20-inch scope, and on the right, we have a plethora of other scopes here. Mainly, we have 12-inch Meade Schmidt Cassegrains on piers. And actually, with really good conditions and with a really good CCD camera, you could make these types of transit observations with 12-inch scopes. Not out of the question. So the one on the left is definitely going to be more sensitive because it's bigger in diameter, and you can have a really good camera on that and make these measurements. But your satellite-based observatories, like TESS, for instance, or Kepler before TESS, are space-based observatories that make this exact type of measurement. Okay, so this is really what you would need to set up like this. You can see on the right there, there's some cameras attached to the back. So setup not too dissimilar from this would be used. I would say this would be the bare minimum. So on the left is an 8-inch telescope on a pier. This is not going to be the best option, and on the right is, I would say, a reasonably marketable CCD. The price of this has come down over many years, but this is actually the CCD I know the best. And I've made exoplanet measurements with that CCD and with a slightly bigger scope, but a very similar cousin to the one on the left. So that's an 8-inch Meade, very common on the market. You can make measurements with bigger ones though. But this is just an example of a much more reasonable setup than a big astronomical observatory, just to show that you can make these really cool observations with relatively little. So the other thing you need to know is your location. Right, so here's a light pollution map of around the observatory at TTU's observatory, and the sky brightness is important. So the one that you see that's highlighted in blue, that's your sky quality meter. It's the amount of brightness per certain area in the sky, and so in this case, the bigger that number is, the better, because it's in magnitude. So we remember that magnitude is negative. The more brighter it is, the more negative it is. So the bigger that number is, the darker the sky is going to be. So comparatively, like for instance, in Brownsville, that number is 18. In the first observatory I ever worked in, it's 17. So TTU's got a pretty good site. It's not the top sites in the world like McDonald Observatory, but good enough to make these types of observations, absolutely. So yeah, that's going to be really important. Dry conditions, you don't want to have a lot of turbulence in the atmosphere. You want wind conditions, which is actually the main reason why we're not at the observatory tonight, is because of wind. It's going to shake the telescope and it's going to throw off the accuracy of your measurement too easily. So knowing where you are and the conditions of your observation location are going to be important. The other thing is the time. So it's important to observe the exoplanet well before and well after it transits, because you don't know, if you're looking for an unknown planet, you don't know if it's going to be partially through its transit. So you want to have a very large baseline. The beginning step is basically knowing when it gets dark enough to observe. So there's actually 3 types of twilight, and it all depends if the horizon is that top horizontal line there. When the sun sets and it's 6 degrees below the horizon, we have what's known as common twilight, civil twilight. And then there's nautical twilight and astronomical twilight, which are 12 and 18 degrees respectively below the horizon. Most sensitive observations occur when astronomical twilight is reached. So tonight it's like 10:23, I think, p.m. So we would still have another 2 hours until a serious observation would start. Okay, so true night begins when astronomical twilight ends, and the real depths of night begin. Okay, so for tonight, sunset was at 8:45. So yeah, we're past sunset now, and right now we're actually currently in civil twilight. This is for Lubbock, of course, and so the bottom number there, 10:24 p.m. That's the time that I would say is a good time to start any sensitive observation, scientific observation. So tonight we would start no earlier than 10:24. The other thing we want to know is the weather. This is the weather from earlier this week. So I think this was actually when the tornado was starting to become predicted. So this is no longer the case, but what you would do is, this is using the National Weather Service. It's a geographical tool that you can just click exactly where you want the measurement to be and on the map, and then you get a plot like this, which is very accurate, I think, relative to some other weather sites. But yeah, having an accurate a portrayal of the weather is going to be important. For instance, the third bar where it says sky cover in blue, that's going to be really important because that's the percentage of clouds covering the sky. Of course, percentage of rain, chance, and thunder is going to be important, but all of these different things are going to come into play. You could also use something called a clear sky chart. So for Lubbock, there is one. For Brownsville, there's not, because this comes from the Canadian Weather Service, and I contacted the guy who is copyrighted there, and he said that Brownsville was slightly too south, out of their range of coverage. So there is no sky chart for Brownsville, unfortunately. Totally, you can make one, but it's basically taking something like this, which is reported and publicly available, and re-rendering it so it's a little bit more visually pleasing. The top chunks are going to be for the astronomer in particular: cloud coverage, transparency, seeing, and darkness. And basically the idea is the darker those squares are, the better. So a lot of these nights, for instance, when it gets dark, for instance, this is night, the first blue under darkness here. So I guess I can't really, I can use my mouse. This would be like sunset, night, sunrise. And you can see like in the middle of the night, cloud coverage is really bad. Transparency is really not good either. And seeing, which is the amount of granulation in the sky, the amount of turbulence that you see on a star, is also going to be bad. So these might be a little bit better, but they're not the best. So basically you're going to try to make a prediction, make a call. Of course, it's also going to be important to know what the object's physical properties are, because maybe, it might be kind of not okay, but the object is still bright enough to see, so maybe it's still worth a shot. So that brings me to the last part of setting up an observation, which is, okay, we're looking for an exoplanet transit. How do we know which exoplanets are transiting? Let's say we want to practice on a known one. Well, this exoplanet transit database is actually really cool because all you have to do is put your location and click the time, and it'll tell you, based on where you are and when you want it to be, in your sky, how many transiting systems we know will actually make a transit that night. So tonight, that's this list. This is every exoplanet we know of in Lubbock sky that's going to transit tonight. And so what I'm going to be looking at is a lot of things. For instance, the time it begins, the time it ends. This is in UT time, by the way, so we have to subtract 5 hours. The duration, so some of them are several hours long, some are only 45 minutes long. The brightness of the star, so the bigger this number is, the dimmer the star is. And the depth. So this is actually delta. This is the thing I was just explaining. So, for instance, the star here is 8.2 magnitude, and look at the amount of difference we're trying to find, right? So sensitivity is going to be really important. I can't emphasize that enough. The 3 red arrows are the ones that are reasonable observational targets for tonight. The reason why I picked those is because you always want your target to be above 30 degrees on the horizon. The lower a target is on the horizon, the more atmosphere it's going through and the more perturbation of the signal there's going to occur. So we want something that's going to be high in the sky for as long as possible. The one I'm going to pick tonight is Gliese 1214b. That one is actually going to be a really cool target because it'll start transiting at 3:54 in the morning, which is a good time for me to start. And it's only going to last 52 minutes. So it'll actually be done before 5 a.m., before astronomical twilight begins for the next day. So this is actually going to be a good target to look at for tonight. This is what I would technically be trying to go for tonight if I was observing. And so let's understand a little bit about this planet. So the star GJ 1214, Gliese 1214, it's a red dwarf star, so it's a lot smaller than the sun. It's cooler. It's only 48 light years away, so that's relatively close for a star system. And the bottom 3 numbers there, its mass, its radius, and its luminosity, are comparisons to the sun. So what that means, the first one there is it's 16% the mass of our sun. Its radius is only 21% the radius of our star, and it's 0.3% the luminosity of our star. So it's a very dim star, but these are actually the systems that we want to look for. A lot of the times we find a lot of transiting planets in these like rocky planets, like the Earth-type planets, for instance, going around red dwarf stars or orange dwarf stars, ones that are cooler and smaller than the sun. The planet itself, so it was discovered in 2009. That's a rendition of it in the back. It's kind of like a really fantastic rendition, so we don't actually know what it looks like, but we can make deductions on it, and that's probably our best guess, let's say, an artistic rendition. It orbits its star every 1.6 Earth days. So imagine that a year is 1.5 days long. The mass of the planet is almost 7 times the mass of the Earth. So it's in a weird position where we don't necessarily know what its surface features are going to be like. Is it going to be rocky, or is it going to be gaseous? The planetary radius is a little over, it's almost 3 times the radius of the Earth. So it's bigger than Earth for sure, but it orbits so close to its star. Now, what we know about this planet is known as the waterworld, right? So the waterworld, that should give something away. It's basically the properties we've deduced from it so far indicate that almost 90% of its mass content will be some sort of phase of water, even though it's orbiting the star very close. It's a very hot planet. So maybe steamy, maybe boiling, we don't really know, but that's the best guess. The star in the center of this picture, this is taken from Digital Sky Survey. The star in the center of this picture, that's actually what the star looks like if you were to take a picture with a really good CCD. For instance, here's like a little galaxy. So this is like what a typical CCD image might look like. What I have here is an image using Stellarium of that same field with the planetary system targeted. And the one thing I should indicate is this is a 8-inch telescope field with the camera that we actually use at the observatory. So it's a similar field of view, maybe slightly smaller because they use 12-inch scopes. But when you're planning your observation, you want to know what stars are going to be in your field, because when you want to measure the brightness of a star, you have to do it in comparison to other stars of similar color. So this is a red star. We're going to look for other stars of a very similar color, see how they change at the same time that my target changes, and compare. If there's any shared characteristics, it's probably because there's clouds or something in the atmosphere, which we can then subtract out. And what you're left with then is the actual change in brightness of that star, right? So we're trying to rule out shared effects. And part of it is preparing to know what's in the sky, what's going to be near our target. And the last thing I'm going to show you, I was going to actually try to show you my own data, but it got a little complicated, and I'll show you why. I found out that I observed this with CTMO, which is the Christina Torres Memorial Observatory. It's in Brownsville, Texas, 2 years ago. So I actually observed this planet. I just never got around to, I kind of forgot that I had actually observed it. I found out earlier this week. But basically, when I looked at the data, so here is an image of CTMO's, one of the images that I took. And you might see a problem here if I say that the plus in the center is where the star is supposed to be. So I got a little concerned because I was like, okay, did I do my astrometry wrong? Did I do my coordinates wrong? The answer is no, because when I looked at the comparison of the same spot, that's where the star is supposed to be. So it moved. But stars aren't supposed to move, are they? Well, they do. And I found out that when I actually measured the expected position to the center of where I found it, it's 21.5 arc seconds away. It's an angle measurement. And if you do a calculation, you say if it moved this far in 22 years between DSS's plate and my image, it moved 980 milliarc seconds per year. And the guy at Data Release 2 says that it's a high proper motion star with this. So I got very close to its actually expected motion. The reason why I can't show you a light curve is because I have to figure out a way. You see how the star moved over top of those 2 little stars there? That means those 2 little stars are going to interfere with the signal that I really want. I have to figure out a way to extract that signal first. So that's where it stands. So the next steps would be, okay, isolate that background star and actually make the transit measurement, which hopefully I can show you in the future. And we've learned a couple of things. So the exoplanet transit observations, they require knowing your hardware and knowing your conditions, having good hardware, having good conditions, and knowing where to monitor for those. Coming up with an observation schedule, knowing how to do photometry with proper image calibration, ruling out errors, figuring out all the sources of your different noise, and et cetera. And finally, you can then make the measurement of those transit observables, and we know that those 4 observables are accessible to an observation like this. So small observatories can support larger initiatives with constraining planetary characteristics, continually observing known ones and perhaps even searching for new ones. So the takeaway here is with careful planning and execution, anyone can observe an exoplanet. I believe that. So that's the end of my talk. Thank you very much.
Thank you, Richard.
Hey, thank you, Richard. Do we have some questions? All right, I see an applause button. several applauses. All right, does anybody have any questions for Richard?
Also,
All right, I have a little follow-up comment to what you're saying. The American Association of Variable Star Observers actually has an exoplanet section. Does everybody know about that organization?
I do, yes.
Yeah, okay. I'm guessing some of our audience might not have heard of them before, but that's an organization that helps pair up amateur astronomers with professional astronomers so that when people want to do observations of things that are very bright and hard to look at with the professional telescopes, they can get amateur astronomers to help them out. All right, does anybody else have a question or anything they want to say?
I can't even see who's in the chat.
What is the name of the organization? I'll put it in the chat. American Association of Variable Star Observers.
So
And they do a webinar series also. All right, we have a question from Obi-Wan. I'm guessing that's not your real name.
I think I know who that is.
So how many exoplanets do we know of now?
So confirmed at this point, last I checked since May 1st, I think it's 4,700 something. But you can actually find this at Massachusetts Exoplanet database that usually updates on maybe a weekly basis, but at least a monthly basis. And majority of those planets are discovered using this type of method. So it's like over 4,000 for sure.
4,389 as of the beginning of this week.
4,389. Okay, so yeah, over 4,000.
But it also says test project candidates is 2,686.
That's like the amount that you. Okay, sure.
My guess is that some of those aren't well confirmed yet.
Yeah, some of them might be. There's certainly more that are considered like candidates that have to be constrained, but the known ones for sure, like 4,300.
Okay. All right. Do we have any other questions? And we don't have that many people here, so feel free to turn on your microphone and just ask if you'd like to.
Anybody here who?
Arian, are you trying to say anything?
What was that?
Are you trying to say anything?
I haven't said it. No. Yeah, I have actually a question locally here. Go ahead.
What would be the smallest telescope with which one would expect?
That's a good question. So the question was, what's like the smallest telescope you can reasonably expect to observe a transiting exoplanet? That's a good question because, it depends on where you are. You can do a lot with a 10-inch telescope in a really good location. I've seen actually, there was a famous case of an astronomer who basically built his own telescope. It was an 8-inch telescope, and he discovered a triple transiting system. So it was like 3 rocky exoplanets orbiting a single star. 2 or 3, I forget, but it was a few years ago. And so I would say 8 inches might be the bare minimum, because anything smaller than that, I don't know if you'll have the light capabilities, light collecting capabilities. But yeah, it also depends on your CCD as well. So you can have like a really good telescope and a not so good camera, and the camera might have too much noise, not enough sensitivity to that type of change. So yeah.
Richard, just a little technicality there. TESS only has a 4-inch.
Yeah, but it's in space. I'm talking about ground-based.
Yeah.
Okay, so if we're going to get technical, then the Hubble Space Telescope is actually a really small telescope compared to how they are in the sky. But that's because, space, there's no atmosphere. And really the biggest problem of any astronomical observation, at least on the ground, is the atmosphere. So you don't need to make such a big aperture for space. Yes?
To piggyback off that question, in terms of location, you showed a value of TTU's observatory and what that was compared to Brownsville's observatory, probably NASA or the location in that area.
Yeah.
What would be the ideal value for any observatory? So like zero light pollution, clear skies, what would that value look like?
Yeah, I guess the best sites in the world. I don't know, Tom, do you know like what McDonald's site off the top of your head, or any of the ground-based sites? Because I think it would be like maybe 30, but I'm not sure.
Sky brightness? No.
Whatever the height.
It's not going to be that much fainter than what we get.
Oh, okay. So 23.
Yeah, because 30 would be 9 magnitudes fainter, which would be like 10 to the 4 times fainter. Right. So
Okay.
yeah, so it's maybe you might do like half a magnitude or a magnitude better at like Mauna Kea or somewhere like that.
Right.
But like McDonald isn't as dark as it used to be because of all the oil field exploration around there. That people are flaring all night now, and it's actually noticeably brighter than it was 10 years ago.
Yeah, and I guess the other thing is seeing, which I didn't go too much into, but like the best sites in the world are going to have less than 1 arc-second seeing, which means basically if you see a twinkling star, the more that star kind of swells up, the worse. So you want that angle to be as small as possible. And like the best site in the world would be like maybe someplace near the Atacama Desert, might have 0.7 arc-second, which is insanely small for some sites. So seeing and sky brightness, yeah, both of those are important. Good question.
Yeah, in terms of like 30, I don't think you would even get into 30 from space because of zodiacal light.
Yeah, you're right. I guess
Yeah.
I never really knew what the limit of that was.
Yeah. Okay. Wait, this.
So it's
Others.
do
Were you
you
gonna say
have,
something, Billy? Okay.
yes, do you have data for other exoplanets from your
Yeah, I have
observatory work?
probably at least a dozen that I can say are reliable. I had never had the time to go through. I was working on something else for my master's thesis, so I just collected a bunch of transits, and I assumed I would look at them someday. So yeah, there's like maybe a dozen and a half, ranging over 4 years. So yeah, plenty of. If anybody wants to ever work on those things, let me know. I can share the data.
What filter do you use for the transit work?
So most of the filters I used were in SDSS, so it would either be R, SDSS R. Sometimes I did Johnson V, but it depended on, for instance, if the field was covered by the Sloan Digital Sky Survey, I had to choose. A lot of them are actually also unfiltered, so there's a very limited amount of work you can do photometrically, but that was back when I was like learning. I basically taught myself how to do it. So I started with unfiltered, the most simple kind of setup, and then added filters, did multi-band at some point, did maybe simultaneous like red and green filters or something like that. But yeah, I think this one, I don't remember actually what the filter was on this one. I have it written down though. So.
All right, and have you looked at using difference imaging? Because you mentioned you had the problem with the star you were interested in having moved on top of another star.
Yeah, so I have a difference image engine that I constructed for my master's work. That was for finding transients, but I think I could just tune it for this type of work. So difference imaging was one of the ideas. Yeah, that's a good idea.
I was just going to ask about that. I just wanted to ask if both those images have similar resolution.
I didn't do much of the DSS analysis. What I did was I just found the reference field and I put it on the slide. But I think that they're comparable enough. The only difference is I took it at higher binning because of the sensitivity. So like I did a 2x2 binning, and there might have to be some adjustments there on resolution.
Yeah.
But
yeah, there are some software packages that can deal with the resolution even being different.
yeah, that's a good point. You give me a lot of ideas.
Okay. All right, do we have any other questions, or should we move to the demo portion of the evening?
So is it the Stellarium?
So there's going to be Stellarium, and then we also have the other science demos that people have set up that are put on the Google Drive. I haven't seen Linka yet, so I don't know if she's going to be there for the Tesla coil one.
She didn't reply, so I'm
Okay, so she might have had something come up. So the Tesla coil one probably is not happening, but you could check in there every once in a while and see if it is. Otherwise, the other demos should be going on in a few minutes. And if you want to do the Stellarium tour with Richard of tonight's sky, and what would be up there if it wasn't cloudy, then he can show you that. And this should be good for the next few days in terms of the objects that you might want to look at. So if the weather does get better, or if you're calling in from somewhere where things are clear, then you could make what he's going to present.
How long for the Stellarium Tour should I give? Because it's like a quarter after now.
I would say do about a 15-minute one, and then if people want to hear more, then they can hear more.
Okay.
Yeah.
Yeah, 15 minutes is fair.
Okay. All right. And I encourage people to check out some of the other demos too. All right. So I'm going to have to drop off to help Arvin set up for his.
Okay.
And a few of the rest of us who are local might have to help people get into the Zoom rooms.
Sure. I'm going to give 2 minutes to break here, and then I'll start.
Okay.
Okay. Thank you so much, Richard, again. Excellent.
Thank you.
Yeah, very, very good job, Richard.
Thank you. Yeah,
Thank you.
absolutely.
To all my audience here, thank you so much for putting up with us. So let me switch this. I'm going to stop sharing for a second. And then I'm going to switch screens. Yeah, no, I didn't mute myself. Just talking to myself here. It's the usual firmware. Share again.
Yes, my favorite's off.
Okie dokie. Yeah, so I'm just going to give it another minute so I can get some water. Oops.
Okay, so I've got Arvin set up on that. Does anybody else need help getting set up for a demo that they're doing?
So, Tom, I cannot find Linka, so should I go ahead and what? Start Zoom meeting?
Yeah, I would just say, I would say just send her an email and say if she does show up to join Richard's one and send you a chat message, and then you'll help her get on there.
Yes, okay. Yes.
Yeah.
Thank you.
Okay. Richard, are you talking to the people in your apartment, or do you mean to be talking to everyone because you're muted?
Dr. Macron, I think he's talking to someone else. I don't know.
Okay. Okay, I think he said he had some visitors right now, so it's probably them.
Richard, somebody should tell him that we cannot see when he points to the screen.
Yeah.
He needs to use the cursor.
Okay.
Do
we want to keep? Do we want to stop recording also?
Richard? He cannot hear us.
Yeah. No, I think he can hear us.
All right, everybody. So, welcome to the second part here. This is, I'm going to show you some of the highlights of what we would be able to see normally tonight. I'm going to.
So, Richard, you're still recording. Do you want?
See with, for instance, at Lubbock, with the telescopes that we have here, so kind of limiting into those capabilities. But as Tom said earlier, this is going to be valid for at least a few days, right? The sky doesn't change too much in those days. And it would also be, if anybody's from like different latitude, like Brownsville, for instance, all you really have to do is look at this plot and shift the sky up or down, depending on if you're higher or lower than Lubbock. So this is going to be pretty close to what you can observe in most of Texas, I would say. So right now, what we would be looking at is if you came out of your house and you were looking due south, this is what you would basically be seeing on the horizon. So zoom out just a little bit here. Not that much. So, right, so the moon right now is basically what we're calling transiting. So if you're looking exactly south and you draw a straight line up from the horizon, that's known as the meridian. And when anything goes from the left side to the right side of the meridian, it's known as transiting. So not to confuse an exoplanet transit, but it's kind of similar in the sense that it's passing across a certain reference point. And so astronomers are looking for objects that pass the transiting point, because that's the highest it's going to be in the sky that night, which means that's the least amount of atmosphere that's going to pass through it. So one thing I want to drive home here is, with the lower you look in the sky, the thicker the atmosphere is. This is exactly why the sunset turns red, by the way, why it's yellow in the sky most of the time. As soon as it gets to the horizon, it's becoming a different color. Same thing happens to stars. So if I'm going to try to make a measurement of something, I'm going to look at it as high in the sky as possible. So here we have a couple of famous stars actually that you can see. Ones that are setting are going to be to the right. So this is like if you step outside and you're looking almost directly above you. You have Regulus and Arcturus, which are on both sides of the moon. And actually, I mean, if this is accurate right now, there's actually a satellite passing in front of the moon, and you can see it going down to the south. I actually don't know what satellite that is, but you could probably tell. So what I'm using is Stellarium, which is free software. And this is actually, so this is almost real time. I'm sure you would see a satellite if you were looking out there right now. It's dark enough. Spica is to the left. That's also another famous star. And then setting to the west, we have Procyon. We have Sirius, the dog star, which is setting now, basically. And so that's like your southern sky. Now, the other thing that you can consider is, and actually I should put the markings up on here, is where the plane of the ecliptic is. So, there's ecliptic. There we go. So yeah, these are really two important reference points. The meridian is the green line that I was describing before. That's like, okay, when is it highest in the sky? When is it the most observable? The other thing, the red line that I just placed, is the ecliptic. Now, the way that you would want to visualize this, since we're looking from the Earth out, we need to understand the geometry. Geometry is pretty much the most important thing for an astronomer, is like understanding the celestial coordinate system. And really, you're looking at a projection on the sky. So what's the real three-dimensional reality? The reality of the red line is you're looking into the disk of the solar system, essentially. So we know the solar system is more or less a plane, and the Earth orbits in that plane with other planets, more or less. Of course, it's not perfect, but the red line is if you're looking into the Frisbee. You're looking into the disk of the solar system. So what are you going to find? Why is the ecliptic important for that reason? You're going to find a lot of objects related to solar system dynamics there. Planets, as reference objects, your zodiac constellations are going to be the ones that are basically bordering the ecliptic. So that's actually why they're famous, is they just happen to be the constellations that are along that line, which change, of course, because the Earth changes over time, like precesses like a top. So the zodiac constellations change in time. You can see Mars is actually setting right now. So it looks like it's high in the sky, but consider the fact that this is the west. Mars is actually low on the sky and it's going down. So you can still see like the top right shoulder of Orion, you see Betelgeuse here. But Mars would be visible at this point if you're not blocked by trees. It's I don't actually know how high it is in the sky. It's altitude. It's out. So that 30-degree limit of observability, it's reaching that right now. So you'd still be able to see it when it passes below there, but observations will become less reliable, basically. Right. So that's Mars there. Mercury is also setting too, but Mercury is usually too close to the sun to see. So it's going to be, Mercury is a very difficult planet to observe because it's so close to the sun. But it's there. It is there. We know it's there. And okay, so other planets in the sky right now, there's actually none, but I think some will be coming up later. So what I'll do, this is like current time. This is like almost 9:30. So if I fast forward in time throughout the night, we can kind of see what's going to arrive. So this is around 11 o'clock. Now, I don't actually see any other planets coming up right now. So you're going to have to at least wait until the wee hours of the morning before Saturn rises. That's the next object that I knew was going to be up, Saturn and Jupiter. So basically around 3 a.m., you'll start to see Saturn and Jupiter. Oops, whoa. Not that, hopefully, that would not be good. Right, so between, let's say, 3 and 5 a.m., you can see Jupiter and Saturn arise in the east, followed by Andromeda and the Triangulum Galaxy on the left. Those are our two closest neighbors, and we're actually on a collision course with Andromeda right now. So I forget what there was this one famous, it's not Kurt Gesagt, it was another famous YouTube channel who called it the Milk Andromeda. He called it a name. You have to look up this video on YouTube. Basically, he was talking about the merger of these two galaxies, and it was the first time I heard the name of both Milky Way and Andromeda said in one. It was almost, we're going to become one galaxy, so we need a new name. But that's going to be in a long time. You don't have to worry about that. It'll look spectacular, and there actually won't be too many stars colliding with each other because space is vast and the distance between stars is generally too big for that to occur. But yeah, so that's the southern sky, and then I'll just end here with the north. Was it? Milkometa. That sounds familiar. Yeah. So the future people on Earth are going to have a problem figuring out the name of this new galaxy, but. This is actually how galaxies, I should say that this is how galaxies behave all the time. So over large cosmological times, galaxies actually wind up interacting with each other. And, when galaxies were first systematically observed 100 years ago, basically, we saw kind of two different types. One's with spirals and one's without spirals, called the elliptical galaxies. And the idea was, spirals are young, and then over time elliptical galaxies are young, and spirals eventually form. But that didn't make sense based on the measurements we started to make, because we saw elliptical galaxies, even though they had no features, they have all old stars and they're not really producing any new stars. Whereas spiral galaxies, the ones that we said were later, are still producing new stars. In fact, peak star formation, we're past peak star formation. Where we are right now is as if we were just born and we're just finished being born right now. So majority of the universe is still ahead of us in terms of time. Majority of the universe is going to be black holes and photons. We're still in the birthing phase, but we're at the tail end of that birthing phase. So we're actually at a very fortunate point, because if we were here, cosmological time in the future, billions of years in the future, eventually we're not going to be able to see any other galaxies. We're only going to see ours. And so future astronomers, let's say we lose all of this knowledge, future astronomers are going to assume we're the only galaxy in the universe, and it will be impossible to find the other galaxies. They will be too causally disconnected because space-time is expanding. So over time, we know that actually spiral galaxies are young and they collide with each other. And so Andromeda is a spiral, it's bigger than us, we're a spiral, we're just slowing down in our star formation, we're just starting to get a little bit older, and they're going to collide. And then another galaxy is going to collide and another galaxy, and eventually that's what happens. And then all the stars die and they become black holes eventually. Either they become black holes or they're absorbed by black holes. So we're at a really cool point in history. Not necessarily sure why, why we're at this particular point in time where things are observable. For instance, we can observe the dark energy expansion of the universe. We know that the universe is not getting bigger and slowing down, it's actually getting bigger and speeding up. But if we existed a billion years ago, we never would have seen it. And if we exist billions of years into the future, we might not actually know that there's, for instance, dark matter. We might not have enough galaxies to observe dark matter. So we're at this really weird time where we can observe all of these different phenomena. And we know that the universe is expanding simply because we can still see the stars. Eventually we won't. Eventually it'll just be a black sky with a couple of stars, and that's it. So, but that's like a trillion years from now. So it's not in our near future, that's for sure. Trying to see here. So I got 4 more minutes. I'll just give you the north sky. The north sky is the north sky is a good reference point. So actually, when you're doing observations and you have like a small aperture telescope, you want to align that telescope typically to the celestial north pole. That north pole changes, of course. So over time, we process like a top. The North Star was not always Polaris. For instance, when the Egyptians built the Great Pyramids, the North Star was Thuban in a different constellation, and that was curious because when we found the Great Pyramids of Giza and we did astronomical alignments, we assumed one of the shafts of the main pyramid was pointing as a meridian marker of the North Pole. But when we look, the North Star is farther away. When you actually go back in time and you calculate what the sky looked like 5,000 years ago, the North Star was Thuban, not Polaris, and it was directly looking out of that one meridian shaft of the Great Pyramid of Giza. So it's kind of interesting to know, but the North Star is our reference point for aligning the telescope and getting things situated where we are in the sky before we make an observation. And the way this kind of works, if I kind of go to now and fast forward, some of these stars, for instance, never set. So if you're closest to this observation, this rotation point here, some of these stars are circumpolar, they never set. So for instance, this star, which is Kochab will never set, but you won't see it during the day when the sun comes up. And this point gets higher and lower in the sky as the seasons progress. So that altitude does change. Some parts of the world start to exhibit different seasons because of this precession going around the sun at an angle. So those two things give us variation in the sky. But precession occurs over 26,000 years, so you don't actually see it on a night-to-night basis. But the ancient astronomers knew about precession way before a lot of systematic knowledge of the sky. So for some reason, it's measurable. And the Mayans knew about precession, the Greeks knew about precession, the Babylonians knew about precession. And they could calculate it well into the future, too. So it's pretty interesting that they knew that thousands of years before us. But yeah, that's like the highlights of the sky. You could look at clusters. You can look at galaxies, deep sky objects, essentially. You could look at stars, which are point-like objects, and there's some interesting systems like those. But then with your clusters, you have open clusters and you have globular clusters. And your open clusters are going to be inside the disk of the galaxy. Like if you're looking within the main disk of the galaxy, and then your globular clusters are going to exist primarily above and below. And they're some of the oldest structures in our galaxy. They're very interesting points of reference. I'm colleagues and friends with people who study those. There's a lot of interesting stuff going on in those clusters. And there's actually some mysteries. I think blue stragglers. Isn't blue stragglers still an open thing? So like we know the age of like these clusters are really old. They shouldn't have any young stars, but these clusters occasionally have a very young blue star, and we don't know why. So there could be somebody in the audience who solves it someday. Yeah, I don't know if there's any questions. That's like the highlights. It's way better in person, of course, but this is the best we can do. Who's here? Am I talking to myself? No, I'm just kidding.
Oh, there's people on.
Oh, cool. Yeah, so are there any questions so far? I mean, any objects you want to look at? Oh, I know what I can do. Yeah, go ahead. Yeah, let's look it up.
I think that's my favorite thing also.
What is it called? Oh, it's the whirlpool? The question mark galaxy. Oh, I like that. And then this is called a justifiable replacement for M51. So this is an interacting system, but yeah, whirlpool galaxy is really cool to look at with a telescope. Yeah, this one's a very resolvable one. So like magnitude 8, like the limiting magnitude for your eyes. I mean, my eyes are really bad, but like in principle, it's like 6 magnitude. So 8th magnitude is 5 times dimmer than that, because each magnitude is 2.5 times in brightness. It's a logarithmic scale. So this one's going to be outside of our naked eye visibility, but with binoculars in a dark site, you could see this. And with a very small, even a refractor, like a 3-inch scope or a 4-inch scope, you could definitely resolve at least this. It won't look like that, but you'll see it. You can see the Andromeda with the naked eye. In fact, that's the farthest object you can see with the naked eye, period, in existence. Like you can't see anything farther than the Andromeda with just your eyes. And if you know where to look, it's bigger than the moon on the sky. It's a fuzzy patch, and it's pretty unmistakable once you find it. So it's pretty cool to see. Like that's a whole another galaxy with way more stars than ours. You just see it in the sky, and it's coming right towards us. So if there's no other questions, the last thing I'll show you real quick is just where, for instance, right now, Gliese 1214 is. So to give you a sense of Gliese 1214, excitedly, is below the horizon right now. Well, actually, no, it's just above the horizon. Yeah, see, it's just coming up, but we wouldn't be able to observe it until like 3 in the morning. So if you follow it and you see this altitude number, it's 17, 18, 19, 20, 21. When this goes above 30 degrees, then I can start to observe it. But it doesn't start to transit until 3 in the morning. So as you can see, right around the time it's going to start to transit, like it's going to transit the meridian right here, basically. So 3 in the morning almost, it's going to be highest in the sky. And that's just before the actual exoplanet transit occurs tonight. So it's going to be, that's why I picked this one, because it's going to be in a really good spot in the sky to observe for maximum sensitivity. So, yeah.
I have a question.
What?
Does this software ever get updated every year? Let's say that any astronomer does any type of discovery and now it's like in the map.
Oh, yeah.
Yes. So
Yeah.
Is it accurate, like the same measurements like every year? If it's an asteroid, let's say, or a galaxy, magnitude changes.
Yeah, I don't know how often they do like established objects, but I know that they have. So this is directly interfaced with the catalog, so you can actually do any astronomical survey you can imagine and overlay it on the sky. Which I actually don't know if I can do it here. Yeah, see surveys. So like you can pick updated surveys as they're updated, and then when you click on one, it'll make like an overlay of the sky. For instance, I won't do it because my computer's like running too many things, but. The other thing you can do is you can do reporting too. So if you find a new asteroid and you can calculate its ephemeris, you can actually upload it here and it gives you those updated it's linked with the Minor Planet Center. It's linked with a lot of like systems that do update, like satellites even. When satellites are decommissioned, that's actually updated on here. New exoplanets. Yeah, so it's pretty good. It's for free. This is amazing. You can control your telescope and your dome with Stellarium if you plug it in and calibrate it properly. So this could run an observatory, and it's literally free, cross-platform OS. Mac OS and Windows and Linux can run it. So yeah, it's pretty cool. I guess I should look at the chat too. I don't see. I guess I didn't. No, what was that? 9:17? No, I didn't hear you guys. Sorry. So okay. Well, I highly recommend checking out the other demos too. So if there's no other questions, I guess that's the end there.
We have a question about whether we'll be scheduling any more of these. I think when the academic year starts back up in the fall, we'll go back to doing these in person. I don't know if you're local or if you know Richard from Brownsville or somewhere else. In June, I think it's not practical to try to do this because we like to try to do these scheduled for observing, but sunset in June is just too late in the evening.
Yeah.
And I think if we start at 10 p.m., we don't expect much of an audience. But we'll check around and see if we have enough students that are interested in volunteering for July and or August.
Yeah. Yeah, and I'll be here, so whenever there's another one, we'll be ready. Yeah, this was great. If I missed anybody's question because I couldn't hear you or I missed your message, let me know. Like, I think the sound system wasn't working for a little while.
All right, and please do go check out some of the other demos that people are doing. Some of them are very nice.
Yeah.
And there should be soon. So the Tesla coil one probably isn't happening, but the other ones should be.
Yeah, and hopefully I have some updates on that data, so maybe I can do a future talk at some point and give y'all an update. Yeah, I appreciate all of your ideas, by the way. That's really important for me to consider for doing the analysis. So.
Yeah, and I think Manuel has a little bit of experience using some of the fancier difference imaging systems.
Oh, cool. Yeah,
If not, he needs to develop that anyway. So,
I have stuff too, so maybe we could just share ideas.
Yeah.
So, if there's, I guess if there's no other questions, I'll probably close this one out. But yeah, there's I think 2 other sessions running, or 1 other session.
I think 3. Let me just
okay, cool.
remind myself. Yeah, so Arvind is doing the sunset and the glass demo. Manuel is doing the spectroscopy demo, and Chesley is doing the pocket-sized solar system, which is really good